Welcome to the engineering class for December the 9th. Before class started, I went and looked on Canvas to see how you guys had done on the homework. And very, very few of you did the homework that was due today. Now, when I saw that, and I said, what the heck is going on here? And then I noticed that when I put the assignment into Canvas, I had forgot to put a due date on it. So maybe that's the reason why you guys didn't do it. I mean, you should have known. I mean, I gave it to you last time. Whenever I give you a homework assignment, it's always due at the beginning of class next time, right? So even though I forgot to put a due date on it, you guys should have done it. But, well, okay, I will admit that I did forget to put a due date on it. So, okay. So what I'll do then is I'll go in and I'll change the due date for it, because it wouldn't be fair if I penalized you, seeing as how I didn't put a due date on it. So let me go in right now before I forget. And what I'll do is I'll change the due date. And what's today? Wednesday. So I'll have it due on Friday. Does that sound reasonable? Okay, so the assignment is labeled Still More Forces. Okay, I'm now changing the due date to be this coming Friday, and I'll have it be Friday at midnight. Okay, so 11:59 actually is the way that Canvas prefers to do that. Okay. All right, so it has now been changed. And also I see that we just got a new person in the class here. So let me let them into the class. Okay. All right, so guys, please do the assignment, the one that's labeled Still More About Forces. I am disappointed that you didn't do it today, but hey, my fault, so okay, won't worry about it. All right, so I'm not going to spend any time talking about the homework then. It's basically the same as what we did last time. It's just I changed the numbers, but not really any different. And we spent the whole period talking about it last time, so I don't think it would be productive use of time to talk about it now. So I'm going to go ahead and launch into the new material for today. So what we're going to do now is I'm going to assume that you guys are now good at taking forces and rearranging the forces and calculating, so that if you have multiple forces all acting on the same point at the same time, you can figure out what the forces need to be so that they all add up to zero. That is the key to being a civil engineer and analyzing forces on structures, is that if the forces don't add up to zero, the structure is not going to stand. It's going to come tumbling down. All right, so what we're going to be doing today is going to be working with structures kind of like this one. Oops, wrong one. Let's try this one here. Okay, so here I'll go ahead and share my screen with you. Okay, so what you see right now is it's a truss bridge. So what we've got is, there are many different types of bridges, but this one here is a very common one. So imagine that we've got a bunch of toothpicks. So, and okay, so down at the bottom here, where you see the blue, that's the river, and that we're trying to build this bridge over. Okay, so imagine that we're making this bridge out of toothpicks, except in reality, obviously, it would be like steel beams or something, or wooden beams. But you can treat them as if they're toothpicks. Okay, so what we're going to do is we're going to take these toothpicks and so the bottom part of the bridge there, the part that people walk on, that's made of two toothpicks. And now normally these guys will be welded together. But if you weld them together, that makes the math way more complicated. And so the way that we can handle it so that we can do the math is we're going to pretend that we have a hole at the end of each one of these toothpicks. And so when we put the two toothpicks together, we line up the hole, and then we put a pin through the hole. Now, normally it would be like a bolt, but we're going to assume that it's just a pin, so that this thing could rotate, right? So there's nothing stopping it from rotating right now. But if I were to take some other toothpicks and put them in there. And so I arrange all these toothpicks like what you see right here. Okay, so so then that's the truss structure that we're going to have. Okay, so like I said, imagine that there's a pin at each one of these places. And by the way, these are called junctions. Okay, so we got a junction right there, a junction right there, and so forth and so on. So everywhere where these toothpick-like structures come together, we have a junction, so that it is free to rotate. So if someone were to stand right here, imagine we have a person standing right there, so their weight is going down there. So if we didn't have this upper structure here, if all we had was these toothpicks there, it would want to go down. And now the only thing that would prevent it from going down is this. I mean, imagine that it did go down. In fact, let me make that be a little bit thicker there. Okay, so imagine that we got this structure going down like that, that structure going down like that. Okay, well, that's not going to be able to happen because that would require these structures to stretch, and they're not stretchable. Okay, so now remember, we're pretending like this top structure is not there, right? So if we have a person standing in the middle right here, okay, their weight wants to make the thing go down. And I mean, it will go down a little bit, but not very much because the structures can't stretch. And so it's only going to go down just a little tiny little bit until the tension of these guys coming up causes it so that it doesn't fall anymore. Okay, but the amount of tension on there would be really, really high. In fact, what I want to do right now is I want to calculate. Let me open up a new whiteboard. So let's suppose that we had a bridge. So here's the one side, here's the water, here's the other side. And so we're going to make a bridge simply by taking two toothpick-like structures that are pinned right there. And we got a person standing right here. Okay. And when they step on it, it is going to sag a little bit. So let's go ahead and let's assume that it has sagged a little bit. So we've got it down like this and over like this. Okay. And so we're going to assume that it has sagged to the point where this angle here is 5 degrees. And we're going to assume that the person standing right here, they weigh, oh, let's say they weigh 150 pounds. So what I'm going to do then is I'm going to draw something called a free body diagram, which if you've taken physics, you say, oh, I know what free body diagrams are, because boy, in physics, do we ever use free body diagrams a lot, but I think that's the first time I've used the term in this class. So a free body diagram is when I draw a picture of what's happening, but then I put the forces in. That's what makes a free body diagram a free body diagram, is I'm going to draw in the forces. And I'm going to draw all of my forces as if they're acting just at this junction. And so even though the person is actually pushing down on the junction like that, I mean, that is legitimate free body diagram, but I'm going to do it. I like to draw my arrows. Oops. Oh, I hate it when I do that. Let me put that back in again. I keep forgetting that I'm in erase mode and not draw mode. Okay, so here we are like that. Okay, and there's my junction. Okay, so let's go back into red. Okay, so the weight of the person, I'm going to put it right here. I like it when I drew my free body diagrams so that the tail of the arrow is on the point where the force is acting. So even though in reality they're pushing down from above, we're going to draw it as if it's the way that I've shown it there. That makes it easier to figure out what's going on. Okay, so we got a downward force, but the thing isn't going to go very far down because it's going to stretch these beams here. So we're going to have a force going up this way. And so I'm going to call this force T, and we're going to have another one over here. It's going to be symmetric. And the reason I'm using T is because T is the first letter in the word tension. And there are two types of forces that we're going to be dealing with for the rest of the year here. If you have an object where you're squeezing the object, so I've got my toothpick and I'm squeezing the object, then we say that the toothpick here is experiencing compression force. If it's being squeezed, it's under compression. If it's being stretched, then it's under tension. All right, so that's what we've got in this case right here. When I've got this this beam, and I'm going to assume that it's attached up here, and it's attached up here. We got some sort of a footing here. And so I've got a pin right here and a pin right here. And so when this person is pulling down on it, that beam is being stretched. And so when you have an object that's being stretched, then we say that it's under tension. So T will tell us how many pounds of tension force this thing is experiencing. All right, so now, if my downward force here is 150 pounds, and if this angle right here is 5 degrees, you guys, based on what we've done over the last couple of days, you should be able to figure out what is the tension force that is necessary in order to make these guys all equal 0. So if we add up all the forces, so this symbol right here is the Greek letter sigma, and it means add them all up. So if we add up all the forces, it had better equal 0, because if it doesn't equal 0, then our bridge is falling down. All right, so what does T have to be in order for these forces to add up to be 0? Now, rather than sit around and wait for you guys to do that, I'll help you with this. Okay, so the first thing you need to do is you need to look at that tension force. And you say, well, that tension force is what Mr. Hendricks likes to call a funky force. Because if a force is purely horizontal or purely vertical, those are easy to deal with. But if it goes off at an angle, then that's a funky force. And funky forces are hard to deal with unless you defunkify them. If you break them up into their components, then they become very easy to deal with. So that's what I'm going to do is I'm going to break this guy into his components. So I'm going to say that that funky red force is the same as these two non-funky component forces. I'm going to do the same thing on the left side. So I'm going to replace those two red funky forces with these 4 non-funky component forces. Now, if T was a number that we knew, what would this X component be? So I'm going to call this X, I'm going to call this X, I'm going to call this Y, and I'm going to call this Y up here. Okay, so if T was a known number, how could we calculate a number for what X and Y are? Well, hopefully, let's say we want to know what X is. All right, so X, so if here's my triangle. So this is T, this is X, this is Y. And this angle here is 5 degrees. I'll tell you what, let's just call it theta for now. All right, so if I'm interested in knowing X, well, I say X, that's the adjacent side. What's T? That's the hypotenuse. Okay, so adjacent hypotenuse, SOHCAHTOA, let's see. Okay, sounds like cosine. All right, so cosine of theta is going to equal the adjacent, which is X, divided by the hypotenuse, which is T. Okay, and I know what theta is, it's 5. So let's go ahead and, instead of writing it as theta, let's go ahead and put in the 5. Okay, and now if T was a known number, I realize now it's not, but if it was a known number, okay, then we could solve for X by just multiplying both sides by T. That goes away. So what we get then is X equals T times the cosine of 5 degrees. And if we did the same thing for Y, we would find out that Y is equal to T times the sine of 5 degrees. That makes sense? Okay, so now that we know that, let's go and here, let me clean some room here so I can do some work. And maybe I'll even get rid of this because I need a little bit of room to work here. Okay, so if it's true that we add up all the forces, it equals 0, we should be able to do that in both the x direction and also in the y direction. So let's do it in the x direction first. Let's say that we want to add up all the forces that are only in the x direction, and we know that has to equal 0. So what have we got in the x direction? Well, we've got this guy here, which we know is t times the cosine of 5, right? And he's going to the left. So let's define our plus direction to be the right, and so our minus to the left. So if he's going to the left, okay, so, well, actually, let's do this positive guy first. So this guy here, he's going to the right, which is the positive direction. So this x here is t cosine of 5. So if we add up all the force in the x direction, we got t cosine of 5, okay? And then we add up this guy here, so minus t times the cosine of 5. So that equals 0. And so t cosine of 5 minus t cos of 5, well, that just says 0 equals 0. So that's a true statement, but it's not helpful at all, okay? So, so adding up the forces in the x direction didn't give any value at all. It just told us that 0 equals 0, and we already knew that. But what if we add up all the forces that are in the y direction? Let's try that. Okay, so let's add up all the forces in the y direction. So what have we got? We got this guy right here, which we know is t times the sine of 5, right? So we have t times the sine of 5 degrees, plus also don't forget this guy right here, which is also t times the sine of 5. So plus another t times the sine of 5. And then don't forget we've got this guy here going down. So if we define that the plus direction is up, and so minus direction is down, so we're going to have minus 150. Okay, so let me just clear some room here to work. Okay, so minus 150, that has to equal 0, because if it doesn't equal 0, our bridge is falling down. Hey, I'm thinking now we've got something that is useful. Now all we have to do is just brush off our algebra skills and we can solve this. So if we add 150 to each side, okay, so that goes away. And we got two of these guys. So if we have one t sine 5 plus another t sine 5 times the sine of 5, so that gives us 2 t sine of 5s. That has to equal 150. So we divide by 2, and we also divide by the sine of 5 while we're at it. So 2 sine 5. Okay, so, and then let me get rid of these so I have a little room to write. Okay, so what that gives us then is that t is equal to 150 divided by 2, and also divided by the sine of 5. Okay, so we can calculate now what is the tension force in that beam. So if I just take 150 divided by 2 and also divided by the sine of 5 degrees, I find out that the tension force is 860 pounds of force, which is a lot. Remember, the person who's standing on the beam here, they only weigh 150. And yet, when that beam sags down, okay, it sags down, and if it sags down 5 degrees, that creates a tension force that's trying to pull the beam apart, and that tension force is 860. So that tension force is way, way, way more than the weight of the person. Now, what if we didn't want it to be 5 degrees? What if we only wanted it to be 1 degree? Okay. What if instead of sagging it down 5 degrees, we only want to sag it down 1 degree? Well, what's that going to do? That's going to change this 5 here, change it to a 1 degree. Okay. And so that's going to take that 860 pound force, and let's see what it does to it. So 150 divided by 2 and divided by the sine of 1 degree. Okay. That force that used to be 860 pounds, that all of a sudden goes up to 4,297 pounds. What if I didn't want it to sag at all? What if instead of 5 degrees and instead of 1 degree, what if I wanted it to be 0? I don't want that beam to sag at all. Well, the sine of 0 degrees is 0. So what is 150 divided by 0? Well, your math teacher is going to say it's impossible to divide by 0. But an engineer is going to say, well, if you divide by a number that's so close to 0 that it might as well be 0, the number that you get as your answer is infinity. Okay, so what that means is that if we have a bridge that looks like this, okay, so here's the bridge, here's the water, here's the, or I'm sorry, these are the banks. Okay, so if I have a structure here and another structure here, and I have a person standing on the structure, okay, if these guys are perfectly horizontal so that they don't sag at all, when this person stands on them, the only way that they could still be perfectly horizontal if the tension force in them is infinite, which is obviously impossible. You cannot have infinite force. So that means that these guys are in fact going to stretch, even if they're made out of the strongest metal available, even if they're made out of, I don't know, what is, steel, magnesium, unobtainium. It doesn't matter what they're made of. If you take an infinite amount of force, you are going to be able to stretch something. So it will, in fact, sag down. Whether you like it or not, it is going to sag down. Okay, so if this person stands on this structure here, it's going to sag. Okay, so what we want to do is we want to make it so that it won't sag. So clearly, we need to enhance this structure somehow. And so what we're going to do is we're going to add these beams. Oops, I keep forgetting I'm in erase mode here. Okay, so we're going to add some beams here. So we're going to put a beam here like this, and a beam here like this, beam here like this, beam here like this, and a beam here like this. So now, when the person stands on it, so their weight is trying to pull it down, the weight that's pulling it up is now these guys right here. We don't need to rely on the tension of these beams to hold the beam up. These members right here, they can provide that vertical force that we need so that we don't have an infinite amount of tension in the floorboards. Okay, so this is the reason why we have structures like you see right here. So this is called a truss structure. And you see these truss structures everywhere. Bridges, actually, one common place where you see them is in the roofs of buildings. Now, in a normal building, the ceiling makes it so that you can't see the structure inside the roof. But if you go into a really big warehouse, if you go into a grocery store or some really big store, they usually leave the ceiling unfinished so that you can look up and you can see what's inside the roof. And what you'll see is there's a truss structure there. Truss structures are used everywhere. And now you know the reason why you have the truss structure, because if you didn't have this structure up on top here, if all you had was this lower part, any weight at all would cause an infinite amount of tension in these beams, and they would fail. So by putting this truss structure up on the top here, then that makes it so that the thing is a lot stronger. Okay, so what you're going to do for your homework tonight is you're going to analyze the forces in a truss structure. And I'm going to walk you through. So we're going to do it together. And then tonight you have a couple problems you're going to have to do on your own. So these angles here could be pretty much anything one. It depends on how long we want these beams here to be. So there's a bunch of ways that we could do this. We could make a truss structure that looks like this. Okay, so if this is the bank of our river, here's the river, here's the other bank. So we could make our structure so that we keep these guys relatively low, because you know, the metal they're made of is pretty expensive. So that's one way that we could do it. And the other way that we could do it, you know, here, so here's that same river, here's the bank. What we could do instead is we could make these guys really tall. So our bridge is going to look like this. Okay. Now, the fact that these guys are so tall means that this bridge is going to be much more expensive, because the longer the beams are, the more it costs to buy them. So a tall bridge is going to be really expensive, whereas a short bridge is going to be less expensive. So you would think that a short bridge here would be the obvious way to go, but we might run into some problems. Let's see what happens if we run into those problems. So if we've got a short bridge here, okay, so if we look at these angles here, let's suppose that this angle here, oh, let's say it's 10 degrees. And this angle here, just, you know, you can see it's a little bit smaller. Let's say it's 5 degrees. And so this angle up here, so in fact, let me go back. My picture here is not the greatest picture. Let me go back into this picture here. So let's suppose we want this to be a short bridge. Now, the way that I've got it drawn here, this angle here, the thing, oops, sorry, wrong way. I have to turn on annotation before I go touching it. So this angle here is smaller than this angle here. So let's say that this one here is the one that's 5 degrees. And let's suppose that this angle here is 10 degrees. Now, obviously, the picture here doesn't quite match the numbers, but let's just say we can do that. Okay, so what would this angle up here have to be? Somebody help me out. If you have a triangle, if you add up all the angles on the triangle, what number do they have to add up to be? Somebody help me out.
180.
180, very good. Okay, so then this angle up at the top here must be whatever 180 minus 15 is. So, okay, so I'm thinking 165. Okay, so let's suppose that the bridge itself weighs 150 pounds. Okay. Okay, so we don't need to have a person standing in the middle here. Just the bridge itself weighs 150 pounds. And so what you can do is you can treat it as if all of the weight of the bridge is acting at the middle point of the bridge. So if I want to analyze the forces on this bridge, if I do a free body diagram, I can treat it as if there's 150 pounds right there. So that's the total weight of the bridge. I can treat it as if it's all acting at that point right there. Now, the supports over here, they have to provide an opposite amount of force. And so hopefully you can see just from symmetry that half of the weight of the bridge is going to be supported on the right side, and half of it's going to be supported on the left side. So I'm going to have a force here of 75 pounds and a force over here of 75 pounds. So you can see the total downward force and the total upward force are the same. Okay, so here is my free body diagram of all of what we call the external forces that are acting on the bridge. I've got the weight of the bridge in the middle pulling it down, and I've got the two supports pulling it up. So those are the external forces. Now, what I want to do is I want to analyze what are the internal forces on the bridge. I want to know this piece right here that I'm calling member A. I want to know, is that member in compression or tension? And I want to know how many pounds of force is it equal to? And then I'm going to ask the same question about member B, member C, and member D. So two questions. I want to know, is it in tension or is it in compression? So that means, is the member being squeezed or is it being pulled apart? And I want to know a number. I want to know how many pounds of force, how many pounds of tension force is it experiencing, or how many pounds of compression force is it experiencing? Because maybe the thing can't handle that much. You know, if I've got a toothpick here, you can see very clearly, you know, with the toothpick, if I go to pull it apart, it can withstand that pretty well. But if I squeeze it together, you see what happened? When I tried to squeeze this thing together, it buckled. So most solid members are like that. Most things that are made out of wood or metal or something like that, you know, they can withstand a certain amount of tension force. They can withstand a certain amount of compression force, but the amount of tension force that they can withstand is different than the amount of compression force. So if I'm going to build a bridge, it's very important that I calculate ahead of time how many pounds of compression force each piece in the bridge is going to experience, how many pounds of compression force is going to experience, and then I need to make sure that whatever materials I use to make my bridge out of, I need to make sure that they can withstand that much force. Because if they can't, this bridge is going to come tumbling down. And so this is what you guys are going to do in the homework tonight. Okay, so first thing let's do is, oh, every time when I stop sharing my picture, all my notes go away. That's annoying. Okay, so tell you what, let's open up a whiteboard. Here's a case where I think it's easier to work in a whiteboard. So what I'm going to do is I'm going to just focus in on the right side of the bridge for right now. So let's imagine, so here's the bank of the river, and here's the river, and here's my one piece, here's my other piece, and there's more to the bridge. You know, there's also pieces here and pieces here, but let's not worry about them right now. Let's focus all our attention on this joint right here. And let's see if we can analyze the forces that are acting on that joint using the skills that we've learned over the last week. So first thing I want to do is I want to do a free body diagram showing only the forces that are acting on the pin that is at that joint. So hopefully you guys remember that one of the forces that's acting there is the ground pushing up, because, you know, remember the bridge over here weighed 150 pounds. And so half of the weight is supported on the right side. So we got 75 pounds over here, and then we got another 75 over on the other side. All right. Now, if we want, so that if we need it so that if we add up all of the forces in the y direction, it has to equal 0. So if we've got an upward force from this guy, the only way that we can balance that is if this guy is exerting a downward force like that. Okay, that's the only way that we can have a downward thing that would cancel out our upward thing. Now that's a funky force. So what do we do with funky forces? We break them up into their components. So those two blue arrows that I just drew accomplish the same job as that one red arrow. And they're a lot easier to work with. Okay, so if so the first question I need to ask is this member right here, which I'm going to call this guy member A. So my first question to you guys is member A experiencing tension or is member A experiencing compression? So I want you guys to type into the chat box right now. Okay, based on the drawing that you just saw, and in fact, if you want, I'll put it back up again. I want you to type in the chat box. And by the way, type it in a private message, not a public message, so that only I can see it. And I'll go ahead and I'll put the drawing back up again. So member A is pushing on the joint. So does that mean that member A is it being compressed or is it being pulled apart? Okay, now I need everybody to answer, please. So it looks like everybody is in agreement that it is under compression. Okay, very good. Okay, so you are right. Okay, so if this is my hand, so if this popsicle stick is pushing on my hand, well, that means my hand must be pushing back. Those of you that have had physics, you know about Newton's third law. For every action, there's an equal and opposite reaction force. Okay, so if the popsicle stick is pushing on the hand, that means the hand is pushing on the popsicle stick. That means that the popsicle stick is under compression. Okay, so in the homework tonight, well, there's the first question is we recognize that member A is under compression. So let's just make a note here that it's under compression. Okay, now I want to know a number. Okay, so I'm going to put F right here, and I'm going to call that FA. So that's the force that member A is experiencing, and I want a number for that. Okay, well, I need to know the angle. So this angle right here, what did we say it was? 5 or 15? Let's suppose that this angle here is, I think 10 is what we said. So tell you what, let's just pick a number and let's decide. So let's say that we decided that this angle is 10 degrees because we wanted our bridge to be really short, because we know that if our bridge is really tall, then it's going to be an expensive bridge. And so we're trying to save money. So we want the bridge to be short. So this angle here is 10 degrees, right? So that means that this angle here is also 10 degrees. How do I know that? Well, if you've got two parallel lines cut by a transversal, this angle here and this angle here, remember what we call those? We call those alternate interior angles. Yeah, and we know that those two angles are equal to each other. So if this angle here is 10 degrees, okay, if this is X and this is Y, then hopefully you've done enough problems now that you recognize the pattern. So hopefully you recognize that X is going to be whatever FA is times the cosine of 10 degrees. And hopefully you know the pattern there. Oops, let me get rid of this. Okay. So following the same pattern, hopefully you realize that Y is going to be whatever FA is times the sine of 10 degrees. You should have done enough homework problems by now that you recognize that pattern. All right. So what we're going to do then is we're going to say, well, since we know that the total amount of forces in the y direction has to equal 0, right? We know that if that's not the case, this bridge is going to be falling down. So that means that this upward force here and this downward force here must be equal to each other. That's the only way that the total forces in the y direction can be 0. So that means, so the upward force, which is 75, must be equal to the downward force, which is FA times the sine of 10 degrees. Make that a little bit more. Okay. And I'm thinking we can now figure out what FA is. Okay. So if we divide both sides by 10 degrees, by the sine of 10 degrees, okay, then that means that FA must be equal to 75 divided by the sine of 10 degrees, okay? And so 75 divided by the sine of 10 degrees, that is 432 pounds. Okay, so you see how it works? Okay, so then what I do is I look in the book to see, all right, what material would this guy have to be made of so that he could withstand 432 pounds of compression? That's a lot of compression force. So yeah, some materials might not be able to withstand that much compression force. You know, like woods may have a little bit of trouble, but metal should be okay. All right, so in your homework tonight, that's what you're going to do. So now we know what is the force in FA. In fact, so let's make a note here. So we're going to make a note of all of the different forces that are in each of these guys. So what we're going to do then is we're going to say that FA, the force in member A, is equal to 432 pounds of compression force. Okay. Now, what about member B? We need to do the same thing for member B. We need to figure out whether he's under tension or compression, and we need to figure out how many pounds of tension or compression he's under. And so the way we're going to do that is we're going to recognize that if we add up all the forces in the x direction, it has to equal 0. So I see I've got a force right here that's going to the right. And member B, you know, he can only push or pull. He can't do anything other than push or pull. And so what that means is the only way that he can balance that force is if he is pulling. And let me make that force be a thicker force there. The only way that we can have all of our forces equal 0 is if member B is pulling on the pin. Okay, so if member B is pulling on the pin, then does that mean that B is under tension, or does that mean that B is under compression? All right, so everybody please type in the chat box. Okay, it looks like everybody's in agreement that member B is under tension. Okay, so if he's pulling on the joint, that means the joint is pulling on him, Newton's third law. Okay, so if he's pulling on the joint is pulling on him, that means he's under tension force. Okay, good. So that's the first thing that we need. Now, the second thing we need is we have to figure out how many pounds of tension force is he under. And hopefully you guys realize that that's not going to be too hard to do, because we can see that if we've got a horizontal force here and a horizontal force here, the only way that they can add up to 0 is if they are equal to each other. So that means that FB must be equal to whatever this guy is, which we said was FA times the cosine of 10. Now, when we first went into this, we didn't know what FA was, but now we do. Now we know that FA is 432. So if I just take 432 times the cosine of 10, I get that FB is 425. Okay, so now I know how much force member B is experiencing. And so let's go ahead and add that to my list up here. So I'm going to say the force in member B is 425 pounds of tension force. Okay. All right, so we're making good progress here. But we are not yet finished, because we have some other members that we need to worry about. Okay. What about member C And what about member D? We need to also analyze, are those guys under tension or compression? And we need to analyze how much force are each one of them under. Okay, so if we decided that this guy here is 10 degrees, and this guy right here, we need a number for him. And depending on how long we make these guys, they could be anything we want. So let's pick a number. I mean, last time we talked about them, but let's pick a new number here. So let's say that this guy is 15 degrees, all right? And so then this one here must be whatever 180 minus 25 is, which I'm thinking is 155, right? Okay. Okay, so let's remember these, because when I move away from this page here, those are going to go away. So let me make a note here. So we've got 155 and
You
10.
froze for a little bit.
Okay.
We
All right.
didn't. You cut out when you were deciding on the numbers.
Oh, okay. Sorry about that. Okay, so can you see the numbers that I decided on? Okay, so I've decided that my lower right angle here, I'm going to make that be 10 degrees. My lower left angle, I'm going to make that be 15 degrees. And so then my upper angle here is going to be whatever 180 minus that is, which I'm thinking is 155. Okay, so now that we know that, now we can come back and we can figure out what is the force in member C and what's the force in member D. And so this is the last part of your homework tonight, right? So let's open up a whiteboard and let's see how we figure out that. Okay, so I want to keep these numbers here. Let me try and clean this up a bit. Okay, so what I'm going to do now is I want to just focus your attention on the upper joint, the joint that you see right here. So right here. Oops, I hate it when that happens. Okay, so we've got a joint here and we got a member here and a member here. So this was member C and this is member D. And this angle here we said was 155. This angle down here we said was 15. So hopefully you recognize that that means this angle up here is also 15 because those are alternate interior angles. Okay, so if I focus my attention on this guy right here, I think we can get what we need so we can figure out what are the forces on members C and D. Right, so what I'm going to do is I'm going to do my free body diagram. And so we decided that member A was under compression. So that means he's being squeezed. So I want to know what are the forces that are acting on the pin. So if member A is being squeezed, that means he is going to be pushing on the pin. So my FA is going to look like this. And I know that that is 432 pounds. Okay, so member D, he can only exert a horizontal force. He can't exert a vertical force. He can only do horizontal. The only thing that can exert a vertical force here is member C. So if force A is pushing up and to the left, then, well, actually just focus your attention on the up. So force A is a funky force, right? So tell you what, let's break him up into his components. Maybe that'll make things a little easier. So if I take force A and I break him up into his components, so I've got an upward component, I got a horizontal component. So if I've got an upward component here, the only way that can work is if I have a downward component. Let me do that in a different color here. Let me do this one in, say, green here. So if I've got a downward force like that, see, if I break them up into its components, the only way that everything can work out is if I have a downward component here to balance out the upward component here. So now I know what's happening with member C. I know that member C is pulling on the joint. that means the joint is pulling on him. So again, I want you guys to vote. So is member C under tension or compression? Okay, looks like everybody's agreed that's under tension. Okay, very good. All right, so let's go back in here. So member C is under tension, all right? And so I know that this downward component right here, let me switch colors here. That green is a little hard to see. Okay. I know that this whoa, I hate it when I do that. Oh, I thought that I had selected draw mode, but I had not. Okay. Let's go back into my components here. Okay, so I know that this downward component here has to equal this upward component here. Okay, and if this angle here is 10 degrees, that means this angle here is 10 degrees. So this upward component here is equal to FA times the cosine of 10 degree. Oh, I'm sorry. It's not the horizontal component I'm interested right now. It's the vertical component that I'm interested right now. So this vertical component here must be equal to FA times the sine of 10 degrees. This vertical component here must be equal to FC times the sine of whatever that angle is, which is going to be the same as this, which is 15 degrees. So I realize this is a fair amount of math, but I think you guys can handle it. So if this guy here must equal that guy there, that means that FC times the sine of 15 has to be equal to FA times the sine of 10. So that means that FC must equal whatever FA is times the sine of 10 degrees divided by the sine of 15 degrees. And I know what FA is. FA is 432. Okay, so I can put that in my calculator. So what I get is 432 times the sine of 10 degrees divided by the sine of 15 degrees. And that gives me 289.8, which rounds off to 290. All right, so now I know that FC is 290 pounds, okay? And I know that it is tension. Okay, we are almost done. In fact, the hardest part is over. So the only thing we need to do now is we need to figure out what is the force in member D. Okay. And then we will be done. And so this is exactly what you need to do for the homework tonight. So if you think I'm going over this too fast, remember that everything that I'm doing here is being recorded. And so I'm going to post this on Canvas before the afternoon is over. And so you can just come back and watch this a second time. All right, so now we need to know what is FD. And once we do that, we will be done. So let me clean up my drawing here a little bit. I've got a mess in my drawing. Okay. All right, so if we look at these components, okay, so actually, let me do one thing here. Okay, so FC here, let me do that one in green. So this is the horizontal component of FC. This is the vertical component of FC. I have not yet drawn the forces for FD. So let's figure out, first of all, let's figure out what direction those forces need to be. So if I've got a horizontal force here from member C that's pushing to the left, and I've got a horizontal force from member A that's also pushing to the left, hopefully you can see the only way that all the forces can add up to be zero is if member D is pushing to the right. That's the only way that everything can add up to be 0. Yes? Okay, so if member D is pushing on the joint, that means that the joint is pushing on member D. So you guys know what's coming. Is member D under tension or is member B under compression? I need you to type it into the chat box in a private message. Okay, looks like almost everybody's in agreement here, but not everybody. Okay, so let me rephrase this. So this is member D. And we've just concluded that the only way this can work is if member D is pushing on the joint. And Newton's third law says that if member D is pushing on the joint, that means the joint is pushing on member D. So it means that member D is being squeezed. So that's compression, not tension, that's compression. Okay, so member D is undergoing compression. Now, how many pounds is it equal to? Well, if we look at this, actually first let me clean things, some things up here. Okay. All right. So this force right here is equal to FA times the cosine of 10 degrees. This force right here is equal to FC times the cosine of whatever that angle is, which is 15 degrees. And so FD must be equal to the sum of those. All right, so if FA is 432, if FC is 290, then we can now figure out what FD is. So FD is 432 times the cosine of 10 degrees plus 290 times the cosine of 15 degrees. So I get 700 and, can't read it without my glasses, 705. Okay, so that means that FD is 700, whoops, sorry, let me erase that. 705 pounds of compression. All right, so there are the answers to the homework. If these were the angles that I gave you in the homework, but what you're going to find is that they're not. I'm giving different angles, but the process that we just went through is the exact same process that you are going to go through. Okay. Now I don't want to take any more time doing this. Let me just tell you that, remember how I said that we had two choices? We could have a tall bridge that looks like this, or we could have a short bridge. So let me put both of them side by side. Okay, so what we could do is we could have a bridge that looks like this, that's relatively short, or we can have a bridge that looks like this, that's really tall. Okay, so this one is obviously going to be very expensive. Would help if I could spell expensive, right? Let's try it again. Okay, but when you do the math, you'll find out that if you make your bridge too short, then the force in member D becomes very high. In fact, if we go back and look at the one that we just did here, you'll see member D has 705 pounds of compression force. So remember, the bridge only weighed 150. Okay, so here we've got a bridge that only weighs 150 pounds, and yet member D is going to have a force in it of 700 pounds. That is going to be a lot, and that's probably going to be too much. And so that's probably going to make the thing collapse. If we instead use longer beams here, then what you'll find is that FD becomes much smaller. Okay, so Shorter bridges are good because they're less expensive, but they're more dangerous because the forces in them, especially on member D, but the others as well. The other ones also, you'll find that the forces in them is much higher, but especially member D here, that force becomes so great that the bridge might collapse. So it's better to spend a little bit more money and make a bridge that's a little bit taller. And then that way the bridge is less likely to experience what we call structural failure. Okay, so in your homework tonight, what you're going to see is you're going to see a bridge that looks exactly like this. In fact, this is the bridge that you need to work with. And so I give you a couple different numbers. I give you, in the first one that I assigned to you, theta 1 and theta 3 are relatively small numbers. So that corresponds to a bridge that is just a short bridge. And so then you have to go through and you have to calculate what are the forces in member A, B, C, and D. Okay. And then the second time around, I give you numbers where theta 1 and theta 3 are much bigger numbers. So that corresponds to a bridge that is much taller. Okay. And what you're going to find then is that the force, especially in member D, but not just member D, others as well, but especially the force in member D, you're going to find out that force is a whole lot less. So basically, that's what you need to do in tonight's homework. All right, so I recognize that we went through a lot really fast. I know full well that some of you are sitting there saying, wow, I couldn't follow that because you went through it too fast. Remember, this is being recorded. I'm going to post this recording on Canvas. So go back and watch it again and do a little bit and then pause the video and do the math and then start the video up again and then pause the video again and do the math. That's the beauty of teaching online here. This is where teaching online is actually better than teaching in person because the online lessons are recorded, the in-person lessons are not. So I know a lot of people don't like online learning, but hey, it does have some advantages. Okay, are there any questions?
So you'll post the video on Canvas to go over it again?
Yeah.
right.
So immediately, I can't post it right away because I have to teach another class. But by about 5 o'clock tonight, so after you guys eat dinner, the video will be posted on Canvas by the time you finish dinner tonight. So if you wanted to work on this this evening while it's still fresh in your mind, I would definitely recommend you work on it this evening. Now, this assignment that we are talking about right now, this is due at the beginning of class next time we meet. Don't forget that the other assignment, the one that you were supposed to have done today, but I forgot to put a due date on it, that needs to be done too. And I put a due date on that one of Friday. Okay, so don't forget, you've got to do those two assignments. Okay, well, if you want to go ahead and type buy in the chat box, then that would be good. If you have a question and you'd like me to turn off the recording so you can ask your question without being recorded, I can certainly understand that. Here, I'll go ahead and turn off the recording right now.